All right, let's see if we can do it. So we're going to do this from a very abstract perspective. So what I'd like to do here is I'd like to start out with some function here. And let's just call this function f, right? And I'm going to begin at some point on this function. I've got to pick some like anchor point that we're going to be looking for that tangent line at. In this picture, it's the point on the left. So I'm going to pick this point, I don't know, I'm going to pick it right here. I'm going to call that A, all right? And if I call that A, then this point right here on this graph is a point, right? It has an x and a y coordinate. What is the x coordinate of this point? What's the x coordinate? Just A, right? That's our x coordinate, is just A, right? And then what would the y coordinate be? So how high would this point be? Well, it would be whatever we get when we take that and plug it into the function, which I don't know what the function is. It's just arbitrary at this point, yes? So wouldn't this be f of A? Any questions you need to ask, okay? That's okay with everyone? Okay, now I'm going to pick a second point, which is going to be the point to the right that I'm going to eventually slide over, right? Now that point, I can call it anything. It would kind of make sense if I called it B, right? We don't though, we call it X, all right? So there's X, and that's right there, that's this point. And it has an X and a Y coordinate as well. What is the X and Y coordinate of this point? X is the X coordinate, right? And the Y coordinate is? F of X, which again, we don't know, but if somebody gave us F, we would be able to actually get these points, right? Everyone agree? Yes. Okay, so like, if a specific example was given to us, right? We'll not do that yet. All right, so we got that, yes? Yeah. All right, now let's draw the line connecting these 2 points. There's a line that connects these two, right? First day of class. Do you remember me talking about you need, if you have 2 points on a line, you need to be able to find the slope of the line between those and the equation of the line between those. Remember us doing that? Mm-hmm. Okay, it was for now, it was for this. So I do have 2 points, don't I? Yeah. So let's first talk about what is the slope, m, right? That's what we use for slope. What is the slope of this? And I'm going to put SEC. It's the slope of the line that, it's a secant line because it connects 2 points together, right? What is the slope of that?
F of x minus a over x minus x.
F of x minus, so wait a minute, hold on. It's rise over run, right? It's rise over run, or there's a formula for it. It was like y2 minus y1 over x2 minus x1, right? Doesn't matter how you do it, but it should be this y coordinate minus that y coordinate, right? F of x minus f of a over, that's your rise, right? That's your rise, over your run, which should be the difference of the x coordinate, so x minus a. That's it, right? That is the slope of the line connecting those 2 points, right? So this right here is the slope of the secant line connecting a f of a to x f of x. Right? That's what that is. It's just, so like if somebody actually gave me a function, right? If somebody actually gave me a function and gave me what these 2 points were, then that would be a number, wouldn't it? It would actually give me that pitch of that line. Okay. I'll show you one more thing I had prepared before class so that way we really make sure we're on the same page here. Where's my Desmos? So here's a picture. I can't zoom in a little bit. So there's a graph. Do you see the graph in red? That's my function. I've picked this point on the left and then a second point on the right. And if I slide, let me see, got to make sure. Nope, moving the wrong point. If I slide the point on the right, you can see, do you see that I have the computer calculating the slope of that secant line? It's calculating it for me. Right now it's 1.8. Further to the right I go, it gets steeper. But as I come this way, I'm calculating. So given any point to the right, I'm going to have some slope of that secant line. It's going to keep changing, right? All right, we have created the formula, right? This is the actual formula for the computation of that number, 2.7901. We've come up with a formula for that, okay? Now, what is the equation of the secant line? Well, let's go back again to college algebra. This very, very useful formula, I told you we would use it a lot. Right? That is our point slope formula for a line. If somebody gives me a point and the slope of the line, I can come up with the actual equation of the line, right? But you need the slope and the point. Do we have the slope of the secant line? Do we have its slope?
Oh, yes.
Yeah, that's it right there. Do we have a point on the actual line?
Yes.
Yeah, we actually have two of them. We have this one or this one, right? I'm going to use this one because this is the point that's not going to move, right? This one's going to be anchored here. This point is eventually going to slide over. So I would write y minus, what would y1 for me be here? What's the y coordinate of that point that's not moving? F of a. Equals, what's the slope of this secant line? Yes, it's going to suck. It's all of this, right? It's all of this, okay? It's f of x minus f of a over x minus a, right? And then parentheses, x minus what? A. Yeah, it cancels. Don't do the canceling. Leave it like that. That is the equation of the line. Does everyone agree with this? Everyone agrees with this, yes? What you're saying is if we cancel, right? Do y'all see that the x minus a's would cancel? Don't do this, but hold on. If I cancel the x minus a's, right, I would get y minus f of a equals f of x minus f of a, right? That's what I would get if I cancel those. And then wouldn't the f of a's cancel? And then wouldn't you just get y equals f of x? And that's true, isn't it? But who gives a shit, right? That doesn't help us do anything. It just verifies that y is the function, right? The y value is the function at x. So even though we could do it, we don't want to because this is our expression. Yes?
Is the left point always going to be stationary, or could that also slide over to the right one?
You could have said, let's leave this one here and move this one to that one.
And use those points.
But the difference, I guess the thing is, we want to know from the picture, we want to know the slope of the tangent line, right? And that's at a single point. Which one of these you want to do it at is up to you. The way I've drawn this is that A is going to be our anchor point. Okay, so it's going to be this one, and we're going to slide this one here. If you wanted to, you could move the x to the other side and slide it in from that side. Doesn't matter which side this x comes from, the right or the left. Hey, wait a minute, that sounds like a limit, doesn't it?
Yeah.
Okay, but eventually we're going to move this, right? So where you put this A doesn't matter, just this one's not moving, okay? Does that kind of address your question?
That makes sense.
Okay.
Thank you.
And I think you've just led us exactly into the whole idea here now, which is if I want to find the slope of the tangent line, how is it different than the slope of the secant line? I mean, there's not much of a difference. What is it, though? If we're going to try and find the slope of the tangent line, this point can't be here, right? Where does it need to be? Right there, on top of this one, right? Which we technically are not allowed to do, because if you put the 2 points on top of each other, you have no rise, no run. So you have 0, 0, right? So what we need to do is allow this point to come along here and get closer and closer and closer to this without actually ever being that. How can I achieve that? How can I make this point move this way? A limit. Let what approach what? Let x approach a. Look, if I slide this point towards A, this point's going to come along, isn't it? As I move this point over, this point's going to come along. And so the only difference between the slope of the secant line formula and the slope of the tangent line formula is that I have to move the x towards A, which means I just have to put a limit in front of that formula. Limit x approaching A of f of x minus f of A over x minus A. And it's that simple. That is the only difference between these two. A limit. That's it. This is college algebra, and that's calculus. Is that you're moving that point on top of the other one without actually ever letting it be directly on top, but getting it as close as you possibly ever could. We know we're going to get 0, don't we? I'm sorry. We know we're going to get 0 over 0 here. Think about it. If I told you to do this limit right now, your first thing would be to do direct substitution. You would replace x with A. So that would become an A, and that would become an A. So you'd have f of A minus f of A, which is 0, over A minus A, which is 0, which is bad. We need to do some algebra. We need to do some trick. Where here, if I just said, hey, back in college algebra, replace x with A, you would tell me 0 over 0, undefined, you're done. You can't do anything, right? But now we can. All right, that's just the slope. What's the equation of the tangent line? Well, we can use the same formula, can't we? It's actually this exact formula, but replace this with a limit in front of it, right? And that's it. So y minus f of A equals limit x approaches A, f of x minus f of A over x minus A times x minus A. So I'm going to highlight here in this formula, this right here, right? That's the slope of the tangent line, right? That's what this is. This limit has to be done on this. This is not part of the limit. This is in the limit, this is not, okay? So you got to do this limit to get that slope, and then you crank out the rest. Let's do an example, okay? It's time to do an example. We have the formulas we need. This is the big result right here. These two formulas are the big results. But do you understand where it comes from geometrically? Because if you understand the geometric part of it, everything else, I mean, just life's nicer when we can see what we're trying to do, right? Let's do a simple function to start. All right, let's do a really easy function. And let's see if we can find the slope of a tangent line at a certain point. All right. So example. I'd like for us to find the slope of the tangent line at x equals 3 of the function f of x equals x squared. Good old parabola. Our classic x squared parabola, right? All I want here is the slope of the tangent line, right? That's all I want. And I want it at x equals 3. So when I say x equals 3, this is our anchor point. That's that A that we're anchoring everything to, right? So I'm going to use this top formula right here, right? Because that's what I'm being asked for in the problem. I'm not asked for the equation. I'm asked for just this. So it's just a limit, right? I'm going to replace all my A's with 3's. So I'm going to do limit x approaches 3 of f of x minus f of 3 over x minus 3, right? That right there is the slope of the tangent line at x equals 3. Now, do I know the function? Yeah, it's x squared, right? So now I can actually replace f of x with x squared. And do I know what happens when I plug 3 into this function? I get 9. Okay, so this becomes limit x approaches 3, x squared minus 9 over x minus 3. Any questions on where that came from? Questions? Right? For this problem, I'm actually telling you what f is, right? I'm giving you the function. So now you can replace these two things by plugging x in here and plugging 3. Did I see a hand? No? All right, now we're back to the limits, right? Take the limit, x goes to 3, top goes where? 0, bottom goes where? 0, 0, 0. Bad algebra trick. Do you see the algebra? What's the algebra? So this is 0 over 0, so I'm going to do some algebra now. What's the algebra? Factor at top, right? Difference of squares, x plus 3, x minus 3. X minus 3. They cancel. And now let x go to 3, and what do you get? 6. You get 6. Next thing, same problem. Now I'm going to add one more layer to this. So if that was part A, this would be part B. Now find the equation of the tangent line at x equals 3. So is there a whole lot of work that I need to do? Do I need to really do a lot more or no? I just need to do this, right?
Yeah.
But wait, everything in the purple dotted, I've already done, right? Everything here is just what? 6, right? So I just need to figure out what's y minus f of, what? Y minus f of what? 3, which we already know what that is because we plugged that 3 in earlier, didn't we? Equals this in purple, which we know is 6. That's that answer down there. And then x minus what? 3. F of 3 was 9. Over here, let's distribute 6x minus 18. Add 9 to both sides. That's it right there. I'm now going to go to the computer. I'm going to graph x squared. I'm going to go look at the x value of 3 on the graph. And I'm going to go see if I'm going to graph this line. I'm going to see if that line passes through that graph and looks like it's tangent. It should, better. Let's see. Any questions while I'm doing this? Okay, x squared first. Okay, there's x squared. I'm going to need to kind of zoom this a little bit so we can see the point. And now I'm going to actually plot the point 3,9 so you can see it on the graph. Okay, there's the point 3,9. And now here comes what we think the equation of tangent line was. It was y equals 6x. And then what? Minus 9. There it is. Does it look like we did it? Does it look like we found the line that runs tangent to that curve at that point? It does, right? It does. What if we change our anchor point? This anchor point was at x equals 3, right? What if we change it to x equals 1? Are we going to have a different slope?
Yeah.
Are we going to have a different equation? Yeah.
Different points.
Different points. Different. So we had to run through the formula again, don't we? Understand? At every point on that graph, there is a different slope of a tangent line, and thus a different equation. You all doing okay? We still have 15 minutes. I have time for another one. You ready? That's kind of cool, no?
Yeah.
All right, I would like for us to find the slope. Let's do this. Yeah, let's find the slope first, then we'll find the equation. Let's do at x equals 4, of 1 over 2 square root of x. I'm going to start with the graph, okay? I'm going to start with the graph. Since you kind of have an idea of what's going on there, I'm going to start with the graph of this. 1 over the square root of x, I forgot my 2. There's the graph of this function. And I want it at 4, right?
Yes.
What would you get if you plugged 4 into that function? What would you get? 1/4? So do y'all see that black point right there on the graph? I want us to see if we can figure out, let me stretch this out. Let me try and exaggerate this for us. There we go. Okay, so what we're going to try and do is see if we can find eventually the equation of the line that passes through that point and runs tangent to this curve. But let's start with the slope, right? Let's start with the slope of that tangent line. Just by looking at the graph, should our answer be positive or negative for this slope? Negative, right? It looks like we're going to get a negative answer. Okay, but let's do it. So we're going to go to this formula right here. This is like our master formula, right? For the equation, the slope of a tangent line, right? This is our master equation. We're going to replace all the x's with 4's, right? So I'm going to do limit x approaches 4, f of x minus f of 4 over x minus 4. F of x minus f of 4 over x minus 4. Now, because I actually have the function, I can replace f of x with 1 over 2 root x, and then minus, now I can replace, I can plug 4 into the function. When you plug in 4, does everyone comfortable you get 1/4? Yes? Square root of 4 is 2, 2 times 2, so 1/4 over x minus 4. There it is. This is the slope of the tangent line, right? That's what we're finding. That is just the limit. Let x go to 4. What do you get? 0, 0. Algebra time. Who's unsure what to do now? Who's unsure? Unsure? Okay, so this right here is fractions, right? Within a bigger fraction, we call this a complex fraction. Whenever you have complex fractions, what you should try and do first is get a common denominator and put these two together, all right? So let's think about the denominator that these both would need to have. This has a 2, that has a 4. So how about we do where they both have at least a 4, right? So I can multiply the top and bottom of this by what? If I want a 4 down here, I'm going to have to do 2 and 2, right? So that would give them both 4s, right? Now this one has a root x. This one does not have a root x. So I'm going to need a root x on top and bottom as well. So I'm going to go 2 over 2 here, root x over here, and then I'll be able to put them together. Is that okay so far? So when you see fractions within fractions, try this first. So limit x approaches 4. Okay, I'm multiplying this top one here, or this first one by 2 over 2, and this one by root x over root x, which gives me 2 over 4 root x minus root x over 4 root x, and then all of this over x minus 4. They have the same denominator now, right? So you can put the numerators together, the numerator fractions together. So it becomes 2 minus root x, that's your new numerator, over your 4 root x, and all of that over x minus 4. Does this look familiar? I mean, this is something in your homework. You should have done a problem like this in your homework when you were doing limits. What now? It's not a complex fraction anymore, but I've got some stuff here I don't like. Like, not reciprocal, the conjugate, right? Because we see a root, right? You see the root up here? 2 minus root x. We can multiply the top and bottom by 2 plus root x. So I'm going to do it this way. I'm going to multiply this fraction right here by 2 plus root x, 2 plus root x, right there, just like that. That's a 1, right? And then this line still goes across. I'm allowed to do that, right? What's the point, though? Why am I doing it? I'm eventually trying to get this x minus 4 to cancel. This is going to allow it to happen, because I get what right here? My new limit, that first multiplication, I get 4. And then what about the middle multiplications on this top one? They cancel, right? That's the whole point of the conjugate. So then what's this right here? Minus x. So 4 minus x on top. Then I have 4 root x. Then I have this. And do I multiply this through? What have I told you? Not yet, right? Leave these alone, okay? All of this is over x minus 4. Oh man, it's almost there. Do y'all see it?
Yep.
This 4 minus x and this x minus 4 are almost the same. If I factor negative 1 out, they'll cancel, won't they? So I'm going to continue over here. No, I'm not going to continue there. I'm going to continue right here. So I have, let me do it this way. Limit x goes to 4. I'm going to go a little slow here. I'm going to pull a negative 1 out. That's going to give me negative 4 plus x. And then that's over my denominator, which is real ugly. 2 plus root x. That's terrible. 2 plus root x. And then my denominator, this right here, I'm going to write it as a fraction, and then I'm going to flip it and bring it up. Okay, and that just, sometimes that helps students see why it's going to cancel here. Comes up as x minus 4 like this. Do y'all see that these cancel now? Because I pulled a negative 1 out. This and this, right? Yeah, you could always rearrange this and just write that as x minus 4. But the negative 1 had to come out for this to work, right? The negative 1 had to come out. So I still have a negative 1. So limit x approaches 4. Okay, what's still on top? Negative 1. And on the bottom, don't I have all this crap still?
Yes.
4 root x, and then 2 plus root x. Take your time now. Take your time. We're going to do direct substitution. We're going to replace all our x's with 4s. We should no longer have division by 0. No more limit. Negative 1 over. I'm going to go slow. 4 times root 4, right? I'm replacing that with 4. So 4 times root 4 times, in parentheses, 2 plus root 4, right? 2 plus root 4. Okay, what's square root of 4? 2? So 2 plus 2 in here is 4. So I have negative 1 over 4 times square root of 4 is 2 times, that you said was 4?
Yeah. 32.
Is negative 1 over 32? We said it would be negative, right?
Yeah.
That is just the slope, isn't it? That's just the slope of the tangent line. What is the equation? I've got 6 minutes. What's the equation of the tangent line then, if I asked you for that now? So what would the equation be? Tangent line at x equals 4. So we go y minus what? F of 4, right, which is 1/4. I'm going to just write it out, though. It's f of 4 equals, now this part, which was the slope, which we just calculated to be negative 1 over 32, And then x minus what? 4. And then we could plug into our function the 4, which we did way a long time ago, right? When we plugged in 4, didn't we get 1/4? And then negative 1 over 32, and x minus 4. Okay, you could now distribute this through and work with fractions and move everything to one side. I'm not going to do that. I'm just going to put the answer up here. So y minus 1/4 equals negative 1 over 32 x minus 4. There it is. We got it. Do y'all believe that? Who has questions?
It's all right to leave our answer in that.
I'm okay if you leave it like this, yes.
Okay.
I'm okay with this right here. So, I mean, really, this idea, there's nothing new here, right? Like, we've already done limits, right? So we've already talked about how to do this. We're just kind of putting it all together, and now it has some meaning to it, doesn't it? It has some actual meaning. So where's there? Imagine I gave you this problem. I'm just kind of getting us ready for next class, okay? I'm not ready to really get too much into this right now. But imagine I gave you this, and I said, find the slope of the tangent line for this function at x equals 4, x equals 9, x equals 16, x equals 25. I'm doing perfect squares to make the problems easier. X equals 36, right? Then can you imagine the work that would be involved to have to do that for each one of those, right? You would have to run through this limit each time and then get your answer, negative 1 over 32, whatever it is, and then plug it in and if you wanted the equation, right? But wouldn't that suck to have to do that many limits? Wouldn't it suck? Yeah, that would suck. So what we're going to do next time, we'll do more practice first before we go too far, but what we're going to do next time is we're going to say, you know what, instead of doing it at each of these values, why don't we just do it at some arbitrary value, x equals a? And then run through the limit and never replace the a with anything. Just leave the a as it is. And what we'll get here, instead of having a number, we're going to have a formula. And then what we'll do is we'll just start plugging the different values of a into that formula. And normally when we do that, it's much harder to do this in general, but it's worth it because then you have a master formula for that function. In fact, the formula you get here will work for this function. It'll work for any point we give it. So it's like it'd be really nice if we could come up with that formula, right? Okay, we'll get into that later.